Okay, so what if I told you that the very same logic that helps Netflix recommend your next favorite movie could also be used to discover life-saving drugs? It sounds like a stretch, but today we're diving into something called pair input prediction problems, and you'll see it's this incredibly powerful framework for finding hidden patterns in, well, pretty much everything.
So, really, what on earth do movie ratings have in common with drug discovery? I know, it sounds a little random, right? But the connection between them is actually super elegant once you see it.
Because at their core, they're both about filling in the blanks. Just imagine this giant grid, like a massive puzzle. The rows could be drugs, and the columns could be their protein targets in the body. The blue squares, those are the interactions we already know about from lab tests. But all those green squares, that's the huge, vast unknown. And our entire goal is to predict what happens in those empty spaces.
And what's so cool about this grid is that it's everywhere. You can just swap out the labels. Instead of drugs and targets, think customers and products, or viewers and movies, just like we said. No matter what the context is, the fundamental challenge is always the same. How do you use the little bit that you do know to intelligently guess all the rest?
Okay, so let's get into the nitty-gritty here, because here's the twist. It turns out that filling in those blanks isn't just one single problem. There are actually 4 different kinds of unknowns we have to think about, and each one gets a little harder to solve than the last.
All right, first up, we've got what's called IDT. Now, this is the easy case. This is when we're predicting an interaction between a drug we already know and a target we already know. The movie analogy works perfectly. We know you like action movies, and we know you like a certain actor, but you haven't seen theirs action movie yet. It's a pretty safe bet, right? We're just filling in a small, obvious gap.
Next, we level up to IDOT. This is where we take a drug that's in our training set, we know it well, and we try to see what it does to a brand new target that's off our training set. Now things get way trickier because we have 0 history for this new target.
And, as you can probably guess, there's the flip side of that coin. ODIT. Here, we've got a brand new drug, something totally novel, and we want to see how it affects a target we already understand really well. We're stepping into the unknown again, but this time, the drug itself is the mystery.
And that brings us to the final boss, ODOT. This is the toughest challenge of all. A brand new drug meets a brand new target. We have absolutely 0 data on either one in this context. We're truly flying blind, which makes this kind of prediction incredibly difficult.
So we have these 4 scenarios, but what they really boil down to are 2 fundamental concepts that are at the heart of machine learning: interpolation and extrapolation.
Remember our easy case, IDIT? That's what we call interpolation. We're safely inside the green zone, just connecting the dots between things we've already seen. But the other 3, IDOT, ODIT, and ODIT, that's extrapolation. That's when we're venturing out into the yellow and red zones, trying to predict outcomes for things that are completely new to us.
Now, you might be wondering, okay, why is extrapolation so much harder? I mean, it seems kind of obvious, but the reason why is really fascinating. And it leads us to something called the extrapolation trap.
The source material for this explainer uses this fantastic analogy of a fake doctor. Imagine a new patient comes in. The easiest, laziest thing to do is just prescribe ibuprofen. It's a popular drug, it works for a lot of things, it's a safe bet. Well, that's exactly how simple models handle extrapolation. They just fall back on the most common, popular answer. It's safe, but it's not very smart. To put it in that e-commerce world, this is like recommending the same top 10 bestsellers to every single new customer who walks through the door. Sure, you might get a few sales, but you are completely missing the opportunity for any kind of real, meaningful personalization.
And this right here is the whole shebang. The reason this matters so much is that this simple ibuprofen approach totally fails to capture what's called the interaction effect. That's the magic. That's when a specific drug is uniquely perfect for a specific target. Ibuprofen works for a headache, but you need penicillin for a bacterial infection. You lose all of that critical nuance when you just recommend the most popular choice.
So, how do we escape this trap? How do we make truly intelligent predictions that don't just default to the most popular answer? Well, the key is to give the model more context. We do this using something the experts call side information, but we can just call them features. Let's look back at our grid. Without any extra information, a brand new drug is just an anonymous new row. The model has no idea what it is or what makes it special, so its only option is to fall back on that lazy strategy, predict based on what works best on average, the ibuprofen strategy.
And this is the solution. This is how we give that anonymous row an identity. By providing features, things like a drug's specific chemical structure or a protein's unique amino acid sequence, we're telling the model what it's looking at. And suddenly, it can understand the properties of the new thing, allowing it to make smart, nuanced predictions, even for a drug it's never ever seen before. It's a total game changer.
You can see just how powerful this framework really is. It's the engine humming behind so much of our modern world. And it leaves us with one last really exciting thought. If we can truly master the art of predicting these complex interactions, what other massive, grand challenges could we finally solve? What could we unlock next?